8.4, systems of linear equations. We've solved systems of linear equations with multivariables, so now we're going to be using an n by n matrix to arrange them and then use it to solve. We'll have m rows and n columns. So we see the setup over here. We have 3 rows, 1, 2, 3, and we have 3 columns. And then we have a 4th column where our answers will be. So each spot inside the matrix has a number, 1, 1, 1, 2, 1, 3. Rows are your first number. It is row 1. The second number is your column number, okay? So we're in column 1, second number is all 1. J. So each spot is A, I, J. So it indicates that it is the ith row and the jth column. So when we use a matrix to represent a system of equations, we only write the coefficients and the constants. And this is called an augmented matrix. So in the given system to your left, we are going to augment it into a matrix. So our first row has coefficients 3, -2, 1, and then 5. 5 is on the answer side, so we put a dashed line to separate the rows and the answer line. Row 2, coefficients 1, 3, -1, answer 0. And row 3, -1, there is no y, so we put a 0 in that column. 4, 11. So we see we have 3 rows by 4 columns. This is a 3 by 4 augmented matrix. Rows by columns. So let's just write the augmented matrix of the system of equations. We see there are 3 rows. We have 3 different variables and an answer. So we are going to have a 3 by 4 matrix. Okay, so let's start filling it in. Row 1 goes 6, -2, -1, 4. 1, there is nothing for a y, so column 2 is 0, 3, 1. Row 3 has no x, so it is 0, 7, 1, 5. So the whole point of using a matrix is to simplify it to solve for the variables. So we're going to be using what's called elementary row operations. So we can do the following 3 items. Add a multiple of one row to another, multiply a row by a non-zero constant, and interchange 2 rows. Doing any of these operations does not change the solution. The goal is to get z, which is our 3rd column, solve for, and then use back substitution to find the others. Okay, so to add a multiple of one row to another, we're going to write r, whatever row it is, plus k for constant, rj, and that will give us our new row I. To multiply by a non-zero constant, we take k for constant times rj I, whatever row it is. And then to interchange the rows, our third performance operation, we just go Ri to Rj, and you have the double arrow in between. So using elementary row operations, we want to get this into row echelon form. And our matrix will look something like this. So this is like our X, Y, and Z. We have Z to a coefficient of 1, and so it's going to be 1Z equals a number, and then we can plug it back in and find our Y, because we eliminated the X from row 2. And then once we find the Y from row 2, we can plug in our X, our Y and Z, and find X into row 1. So it must have a diagonal of 1s, and then zeros underneath the 1s. So row echelon form, and then there's also reduced row echelon form, which is further finishing the matrix. The first non-zero number in each row is 1. This is called the leading entry. The leading entry in each row is to the right of the leading entry in the row immediately above it. All rows consisting entirely of zeros are at the bottom of the matrix. And then to get it into reduced row echelon form, I don't know why I spelled following wrong. Every number above and below each leading entry is 0. So reduced row echelon form. Has only 1s on the left side, 1s and zeros on the left side, and numbers on the right side of the augmented matrix. Therefore, you don't need to use back substitution to find X, Y, and Z. So to use elementary row operations to put a matrix in row echelon form, we have some hints. We're going to start by obtaining 1 in the upper left corner, and obtain zeros below the 1 by adding appropriate multiples of the first row to the rows below it. Then we need to obtain a 1 in the next row, and then obtain 0 below it, and so on. At each stage, make sure that every leading entry is to the right of the leading entry above it. We can rearrange the rows if necessary. And you continue this process until you get into a row echelon form. Once an augmented matrix is in row echelon form, we can solve the corresponding linear system by back substitution, which we called Gaussian elimination. So let's solve the system of linear equations. So we first need to make our augmented matrix. So we see that we already have a 1 in our upper left-hand corner. So we need to get rid of the 1 and the 3 below it. So we are going to take row 2 minus row 1 and get our new row 2. So row 1 stays the same, 1, -1, 3, 4. And then we take row 2 minus row 1. So 1 minus 1, that goes to 0. 2 minus -1, that goes to 3. -2 minus 3, that goes to -5. And 10 minus 4, that goes to 6. The nice thing about a matrix is you can do multiple steps with different rows. So we're also going to take care of this 3 by taking row 3 minus 3 row 1 and get our new row 3. So row 3, we got 3 minus 3 row 1, so 3 times 1, that goes to 3, so 3 minus 3 is 0. -1 minus 3 times -1 goes to 2. 5 minus 3 times 3, so that's 5 minus 9, -4. 14 minus 3 times 12, I'm sorry, 3 times 4, which is 12, so 14 minus 12, that is 2. Okay, so we now need a 1 in column 2. So we look at 3 and 2. Row 2 has 3, -5, 6. Row 3 has 2, -4, 2. All of these are divisible by 2. And that will give us a leading entry of 1. So let's take 1/2 row 3. And now we are going to take 1/2 row 3. So it goes 0, 1, -2, 1. So now we have this 1 entry, and we should switch. Actually, let's go ahead and get rid of this 3. So we're going to take row 2 minus 3 row 3. Row 1 stays the same. So this stays 0. 3 minus 3 times 1, that goes to 0. -5 minus 3 times -2, so -5 plus 6 goes to 1. 6 minus 3 times 1, so 6 minus 3 is 3. Then this stays. So we now have a 1, a 1, a 1. But they're in the wrong order. So we need to get them in the right order by switching row 2 and row 3. So now we are going to switch row 2 and row 3. So we get 0, 1, -2, 1, 0, 0, 1, 3. So now we are in row echelon form. And we see that in our third column, for z. Z is 3. We see y minus 2z equals 1 from row 2. So to use back substitution, so y equals 7. And then from row 1, we see that x minus y plus 3z equals 4. So we plug in our y and z. So we get -7 plus 3 times 3, that's 9. So -7 plus 9 is 2. X plus 2 equals 4, so x equals 2. So all we have to do is write it as a 0.273. Solving a system using Gaussian elimination, we make our augmented matrix. We use our row echelon form, or we get to row echelon form using elementary row operations, and then we use back substitution. So let's go through one more example using the augmented matrix, row reductions, and then back substitution. So we have our matrix 4, 8, -4, 4, 3, 6, 5, -13, -2, 1, 12, -17. Now, if you look at column 1, none of them are 1s. So we need to see which row is going to be the easiest to reduce. Row 1, 4, 8, -4, 4. Row 2, 3, 6, 5, -13. Row 3, -2, 1, 12, -17. Row 1 is all divisible by 4. So, but we can't divide, but we can multiply by 1/4. So we're going to take row 1 and multiply it by 1/4. Goes 1, 2, -1, 4. Okay, so we have to fill in the rest. Just bring it over. So now we need to get zeros underneath of it. You cannot do the first step and then the next 2 steps in the same matrix. They need to be 2 separate matrices. So we are going to take row 2 minus 3 row 1s to get our new row 2. We're going to take row 3 plus 2 row 1s and get our new row 3. So first row stays the same. Row 2, 3 minus 3 times 1, 6 minus 3 times 2, 5 minus 3 times -1, that goes to +8, -13, oh, I forgot to take that 4. There we go. And -13 minus 3 times 1 goes to -16. That worked out well. Let's go to row 3. Row 3 plus 2 times row 1. So -2 plus 2 times 1, 0. 1 plus 2 times 2 is 5. 12 plus 2 times -1 is 10. And -17 plus 2 times 1 is -15. So if you look at our new row 2, we have 8 and negative 16. Those are both divisible by 8, so we multiply by 1/8. And we look at row 3, 5, 10, negative 15. Those are all divisible by 5, so we multiply by 1/5. Row 1 stays the same. Row 2 goes to 0, 0, 1, negative 2. Row 3 goes to 0, 1, 2, negative 3. So we see leading entries 1, 1, and 1. They're in the wrong order, so our next step, we need to switch row 2 and row 3. And this step and the previous step in green could have been done in reverse orders. You're going to find that happens a lot in matrices. So we have our row echelon matrix. If we were to put this back into a system, we'd have x plus 2y minus z equals 1. We'd have y plus 2z equals negative 3. And we'd have z equals negative 2. This is set up very well for back substitution. Y is going to go to 1. And then we're going to plug in negative 2 for z and 1 for y. So we're going to get x plus 2 plus 2 equals 1. So that's 4 and 1. And so we get z to be negative 3. So just write your answer as a point. Negative 3, 1, negative 2. So as a reminder, the leading variable is the one that corresponds to a leading entry in the row echelon form of the augmented matrix. And just as in every other system, in matrices we have different types of solutions. We could have a no solution, which is inconsistent. And that's when you have, on the left side, a row of zeros equaling a number. 0 cannot equal any number. It's not possible. So that makes it no solution. We could have one solution, which is what we've seen so far. And you could have infinitely many solutions when you have a complete row of zeros on the left and right side of the augmented matrix, because 0 does in fact equal 0. So therefore it is infinitely many solutions. Attached to your notes is an example of a no solution, so please look at that and be prepared for class the next day.